pleasure. No. Okay, so it's a pleasure to. Oh.
Okay.
I will start again because
now it's okay.
I have so many announcements. So it's a pleasure to present Otared Kavian. He's going to talk about some remarks on the Cauchy problem for the Laplacian and Lagrangian control of the Euler equations. Thank you very much, Otared.
Okay. So thank you very much for the invitation and giving me this opportunity to see some of you and talk about a work in progress and an old paper with Thierry Oursin. So I'm going to talk about the following problem. Okay, this is the paper published in 2017 with Thierry Oursin, which contains part of the remarks about the Cauchy problem for the Laplace operator. And it contains essentially the Lagrangian controllability of for the Euler equation. So the problem which is going to be the main part of this talk is the problem of well-posedness for the Cauchy problem of for the Laplacian. So first, for the young people who may not be familiar with the definitions, I'm going to give the complete definition. If you take two topological spaces X and Y and a mapping F from X to Y, we shall say that the problem one, that is to solve F of U equals to B for a given B in the topological space Y, will be said to be well posed in the sense of Jacques Hadamard if the two conditions, the following two conditions are satisfied. The first one is that for any B, there exists a solution and this solution is unique. And the second one is that the mapping which maps B to the solution U is continuous from Y to X, okay? So you see here, F is not continuous. F is just a mapping. In some sense, we require that the reciprocal of F, F minus 1, exists and is continuous. So this is the well-posedness in the spaces X, Y. And whenever either of these conditions is not satisfied, or both are not satisfied, then we shall say that the problem is ill-posed in those topological spaces. So Jacques Hadamard, in fact, has given this definition by giving the following example, which is to solve Laplacian of U equals to 0 in the upper half plane with a boundary condition U of X and 0, so on the real line, which is epsilon times sine of kx. K may be an integer, for instance. And the normal derivative of U is equal to 0. So here I'm using the notation xy as a typical point of the upper half plane. So it is easy to see that the only solution of this equation is the function epsilon times sine of kx and cosine hyperbolic of ky. But now, whenever we take y positive, then we have a factor which is epsilon times cosine of hky, which can be very large if y is large, and no matter how epsilon is fixed. Okay, so this means that in the sense of bounded functions, we cannot solve the equation in a continuous manner. As a matter of fact, if we take x to be the space of C2 functions which are bounded and their derivatives are bounded, and y the cross product of bounded function on the real line, then there is no solution at all. This means that any solution blows up at infinity. Okay. So this is a typical ill-posed problem, which is given usually in all textbooks. And as a matter of fact, the main difficulty of all these problems, is well-posed or ill-posed problem, is how you choose the spaces, the topological spaces X and Y. So a more common example is the classical Dirac problem. Usually we don't think of the classical Dirac problem as an ill-posed problem. But actually it is an ill-posed problem if you take it in the following spaces. If you take the space X as the functions which are C2 on the compact set omega bar, and F a continuous function, then this problem is ill-posed. This means that for it may happen that for some functions F which are continuous, you don't have a solution which lies into this, C2 functions. So here is an example which can be constructed explicitly. So I don't need the detail, but since I'm going to give you the PDF of this talk, you can find it if you wish. So in this case, one defines the function u as this series, which is a function which is in C1, but it is not in C2 because the second derivative in direction 1 and 2 has a singularity at the origin. However, if one chooses the spaces X and Y to be the space of Holder functions of order alpha, this means that the functions which are C2 and the second derivatives are Holder continuous of order alpha, and the space Y is the space of continuous functions which are Holder continuous. Or if you take X as the Sobolev space H10 of omega and Y to be H-1 of omega, then it is well known that the problem is well posed, the solution is unique, and you have a continuous dependence of the solution in terms of the given data F. Okay. So you see, usually when we have an ill-posed problem, we could ask ourselves whether we can find a couple of topological spaces for which the problem becomes well-posed. Okay, so this is the subject of my talk today, is to find such spaces for the Cauchy problem for the Laplace operator. Okay, so to begin with, consider a smooth bounded domain in dimension n larger than 2 or equal to 2, such that the boundary of the omega is connected. So omega itself is connected and its boundary also is connected. Okay? So first, denote by the operator lambda, which is a mapping from H1/2 of the boundary into H-1/2 of the boundary, which is the dual space of H1/2. The Steklov operator, the Steklov-Poincaré operator, which is defined as being lambda of f is du over dn, where u satisfies delta equals to 0 in omega and u equals to f on the boundary. Okay, so some people call this operator Dirichlet to Neumann. This means that you give a Dirichlet boundary condition and you compute its normal derivative, which is the Neumann data for the problem. But since Steklov and Poincaré have studied the eigenvalues of the operator lambda, I prefer to use the notation, the denomination Steklov-Poincaré. Okay. Now let f and g be in H1/2 cross H-1/2. So f is H1/2 and g is H-1/2. So the Cauchy problem for the Laplace operator is minus delta equals to 0 in omega, so in this set, and we want u to be equals to f on the boundary and du over dn equal to g on the same boundary. Of course, if u is given on the boundary, then there is just one solution, okay? So the other condition, which is du over dn equal to g, is possible to be satisfied if and only if this function g is precisely the image by the Stikloff-Frankauer operator of f. So this problem is solvable in a unique manner and a continuous manner if and only if the second condition, d over dn, is precisely lambda f, okay? So this means that if we define a space, capital H, which is the set of f and lambda f, where f, which is in h1/2, which is the graph of the operator lambda in the set h1/2 cross h minus 1/2, then the problem, the Cauchy problem 4 here, has a solution if and only if the couple fg belongs to the set H, okay? But of course, this is not very interesting because we have given the Cauchy data on the boundary on the whole set of the boundary, not in a part of the boundary. Now assume that we have the same set omega, but the condition, the Cauchy data, f and g, are given only on gamma 0. Since we are assuming that omega is sufficiently smooth, if there is a solution, it is unique by the unique continuation principle. However, it is not easy to find conditions on f and g, a compatibility condition on f and g, so that the problem becomes well posed. This difficulty arises from the fact that if we could extend the data f and g in a canonic manner to the whole boundary d omega, then we could come back to the previous analysis. But since it is not clear how one could extend f or g to the boundary, then we cannot do the same thing as we did before. Okay. So now there is another situation where the problem can be studied in a satisfactory manner, which is the following. Assume that you have a set omega, which is a domain. Okay, here is this a connected domain, and you punch a hole in it. So you extract a small part of this set, which is called small omega, and now the set omega is the complementary of the set omega 0 minus this small set omega. So in this way, the boundary of the omega has two parts. One part is the set gamma 0, and one part is gamma 1. Of course, one could imagine several connected components, but we begin with these two, okay? Then one can characterize the space of Cauchy data f and g, for which the problem, which is problem 6 here, becomes well posed whenever fg belongs to H. So in this case, so we are going to see how this is possible. This can be done. But the previous example, which is here, this cannot be, up to now we are not able to give a satisfactory result about this case. But there is a case where we can do something. This is the case of a rectangle. Of course, here I present everything in 2 dimensions, but one can adapt the method and the result for higher dimensions. So this is not an issue. So assume that we have a rectangle. So gamma 0 is 0p. So this is the length of this is 0p. And the height of the rectangle is L, small l. Okay. So we call gamma 1 the boundary, which is the upper boundary, and the sides of the rectangle are denoted by gamma. Okay. So now we solve the following problem. We want to solve to find a harmonic function in omega such that u and du over dn are given on the lower part of the rectangle on the set gamma 0. But since we want to be able to solve the problem, we give also a boundary condition du over dn on the boundary. So you see here, this is a way to say that the functions the data f0 and g0 have been extended on the red part of the rectangle in some way. F0 is not extended, but du over dn is extended. Okay, by 0 in this case. Okay. So in this case, we can characterize the space H, for which the solution here exists and it's unique, and we have an estimate of the form norm of u in H1 less than this constant time norm of F0 G0. Indeed, the condition we are taking here du over dn is somewhat arbitrary. We could have set the condition u equals to 0 on the red part of the set gamma, or any other boundary condition. Okay, so this means that this condition on gamma is necessary in order to carry out our analysis, but it is not a natural condition. Okay? So once this analysis has been made possible, with respect to the other problem, which is the Lagrangian control, we can ask the following question. Assume that you have a line, which is, I call it here gamma star, this line, and a function or a distribution G star is given on this part, okay, which has mean value equals to 0. Okay, the mean value of G star is equal to 0 on this red line. Now the question is, can we find a couple of functions f0, g0 defined here on gamma 0 such that the normal derivative of the solution on the red line is exactly equal to G star. So if this were a problem in electricity, this would mean we want to obtain a certain density of current on gamma star, which is the function G star. And in order to achieve that, we are free to choose the voltage on the set gamma 0 and the density of the current on gamma 0, okay, by adding some isolating condition on the set gamma. Okay. This can be also seen as a sort of control or approximate control if only the second condition du over dn minus g star less than epsilon is satisfied. Okay. So now this is the questions we ask ourselves about the well-posedness of the Cauchy problem for the Laplacian. But before giving the details, maybe I explain what we are doing about the Lagrangian control of the Euler equation. So again, here I present the result for omega in R2, but as a matter of fact, one can have in any dimension larger than 2. So we have a domain omega, and we take a smaller domain, which is omega 2, whose boundary is denoted by small gamma. Okay, so this is the small boundary. And on the part of the domain, which is here, we want to solve the following problem: Laplacian of psi equal to 0, d psi over dn equals to v on the set gamma, which is here on this part of the boundary, and the normal derivative is equal to 0 outside this part. And we want to be able to find v such that d psi over dn is equal to h on the set gamma. Okay, so this is a sort of control. So you want to achieve something, a normal derivative on the boundary of omega 2 by choosing a flux for psi on the set gamma. Okay, of course, this is not usually possible, because if you take gamma, if gamma is smooth, or if omega 2 is the small domain omega 2, if this domain is smooth, then d psi over dn is going to be a smooth function. Therefore, not all functions h can be attained by choosing a v, whatever v on the set gamma. Okay. Therefore, we can modify this question by asking ourselves whether we can have an approximate control. This means that we can have the function h achieved by d psi over dn at epsilon approximately with epsilon in h1 minus 1/2 norm. Okay. So why did we look at this problem? Because this can be related to the following Euler equation. Assume that this is possible in a continuous manner. This means that you can have, if h is a function which is C1 with values in h minus 1, 2, minus 1/2 on the interval of time 0t, and assume that we can construct this function psi in C1. Okay, in fact, we can do that. Okay, once condition 9 is satisfied by a procedure, it is possible to show that the function psi is going to be C1 with values in H1. Okay. Now, call U of t and x the gradient of this function psi, and P of t and x this function, which is computed directly. Then the pair U and P is going to be a solution of the following Euler equation. Okay, so this is just the function P has been calculated on purpose for you to satisfy this equation. Okay. So in this case, this means that U dot n of sigma is equal to v of t and sigma on the exterior boundary, and on the set, small set gamma, we have u scalar n minus h less than epsilon. So this means that we can have a normal flux on the set gamma, which is precise, which is approximately the function h we have fixed beforehand. Okay. So in fact, this is a control problem for the Euler equation, and such problems have been studied by Thierry Orstan and Olivier Glass. So this is what we have done is a constructive method by using another construction. Okay, fine. So okay, so this is the Lagrangian control. Oh, I didn't. Okay, sorry, I didn't show the result. So the result is that we prove. So this is the main theorem here. We prove that if we consider the problem, which is problem 12, Laplacian psi equals to 0 in omega, d psi over dn equals to v on gamma, and d psi over dn equals to 0 on the complementary of gamma. Then we define lambda gamma of v, the normal derivative of this function psi on the small domain, omega 2 here, on the boundary of the small domain omega 2. Then the image of lambda gamma is dense. So this means that we can have an approximate control, as I mentioned before. So this is just the main results of this part. So we shall see later. Okay. So let me first show the case of the Cauchy problem in a rectangle, for which we can make a complete analysis and find necessary and sufficient condition for F0 and G, which is here. So you see, we have to solve this problem. We want to solve minus Laplacian of u equals to 0 here, and the Dirichlet data is F0 and G0. Okay, so this is what we want to solve. So to do that, first we choose a function G1 in h minus 1/2 of gamma 1. So gamma 1 is the upper side of the rectangle. Okay, so we are, instead of solving the du over dn equals to G0 on gamma 0, we are going to solve du over dn of x and L on this set equals to some G1. Okay, so we change the problem. Okay, now, so it is clear that for any F0 and G1 given, we can solve this problem in a unique manner. Okay, so once this is done, the problem is to find the function G1 on the set gamma 1 such that the normal derivative of dv on gamma 0 is precisely G0. Okay, so if this is possible, this means that the Cauchy problem can be solved. And if we can show that this can be done in a continuous manner, then the problem becomes a well-posed problem in the set of those function F0, G0 for which the condition is satisfied. Okay. So this is the question. Find G1 so that the, oh, here there is a mistake, dV over dN of X and L. This is not 0, this is L, sorry, because it's on gamma 1, okay? So this is the problem. So in order to do that and find the compatibility condition, we are going to denote two sets of Steklov eigenfunctions, which are the following. So psi 0k are functions which are harmonic. The normal derivative on gamma 1 on gamma is equal to 0. And the normal derivative of psi 0k over dN is equal to some constant psi 0k on gamma 0. Okay, so this is the Steklov eigenvalue problem. Okay, and psi 1k is the same problem, but we change the place of gamma 1 and gamma 0. Okay, so for psi 1k, we assume that the normal derivative on gamma 1 is a multiple of psi 1k. Psi 1k is equal to 0 on gamma 0, and the normal derivative is equal to 0 on the set which is red here. Okay. In fact, in this case, since it is a rectangle, we can compute explicitly the eigenfunctions and eigenvalues. And okay, so I give just the formula which gives the eigenfunctions psi 0k and psi 1k, and here k is larger or equal than 1. And for k equals to 0, there are special cases. So the first one is the constant, and the second one is just a multiple of the function y. Okay, so this can be computed explicitly, and the eigenvalues also can be computed explicitly. And mu 0k and mu 1k are both of order of k. Okay. Now, for the functions f0 and g1, which are given, we compute their Fourier coefficients with respect to the eigenvalues. Of course, these functions, psi 0k and psi 1k, are a Hilbert basis of the space which is here. Psi 0k, the set psi 0k for k larger or equal than 0, is the Hilbert basis of L2 of gamma 0 on this set. And psi 1k is going to be a Hilbert basis of functions in L2 of gamma 1. Okay. So this and one can also characterize the spaces h1 half and h minus 1 half in this manner. So h1 half is just you multiply by mu 0k, f0k squared should be finite, while for h minus 1 half, one has to divide by 1 over mu 1k. Okay, so this is just some calculus. It's not difficult. Once this is done, one can write explicitly the solution of 7, the solution of this problem. Okay. The solution of this can be written in terms of, oh, excuse me, it's not 7, is this is a mistake, is the problem which is, no, okay, this problem, this, okay. So the auxiliary problem for 7, okay. Now, once V is computed, we compute dV over dN. So again, this is some calculation. And now we want to have G0 equal to dV over dN. Therefore, we have to satisfy, G0 must satisfy this condition, okay? And you see here F0k is given, so the components of G0k are essentially these things, these coefficients, okay? These coefficients. And from this, we can compute that G1k must be equal to this. And since we want G1 to be in H minus 1/2, therefore we should have this sum finite. Okay, so this gives a compatibility condition on F0k and G0k, which is this this factor sine h of k to the kl. So this is exponential of kl essentially. Okay, so this means that k times exponential of 2kl, this quantity squared, should be finite. Okay, so from this we can define a space which is the space of functions f0 g0, such that this quantity is finite. Okay, and if we define this norm, so this norm is just the norm of S0k in H1/2 plus this compatibility conditions. Okay, so this. And thanks to the computation we made, we have also that the norm of U is comparable to norm of F0 G0 in this space and is larger also than this. So in order for the Cauchy problem to become well posed, the Cauchy data F0 G0 must be in the space where this norm with star is finite. Okay, and okay, from this one can also look whether we can have some sort of stability. You see, the stability depends, in fact, on the factor L. This means that on the height on which we are solving the problem, and this is this can be expected because you want to solve from gamma 0 to gamma 1, and so the instability is something exponential. Okay, so if we make a mistake, an error of order epsilon on the data here, on gamma 1, we shall have an error of order of exponential epsilon times exponential of L. Okay. Well, and the same analysis can be carried out in order to see whether we can attain something on the set gamma star. So I don't make more comment on this. Okay. Now, I have how much time do I have? No one is there. No. Okay.
Yes, we are here.
You have 20 minutes.
How much time do I have?
A little less than 20 minutes.
Okay, so fine. Okay, so now here for the Cauchy problem, which was here. Okay. Okay, let me see this problem. Okay. No. Excuse me, this problem, okay, this problem. We want to solve the Cauchy problem for the Laplacian when the Cauchy data is given on a part of the boundary and the boundary has two connected components, okay? So for the Kaiser rectangle, we had a connected boundary, okay? And in order to solve the Cauchy problem, we had to add some boundary condition on some part of the boundary in order to extend somehow the Cauchy data. But in this case, we are assuming that the Cauchy data is given on a piece of the boundary, and on the other piece, we don't have any condition. Okay. Now, okay, so it's here. Yes. So I presented the result only for the special case of an annular domain where everything can be computed. In a general domain, the same analysis can be carried out, but we cannot characterize the compatibility condition with a quantified norm as we did before. Okay. So here, assume that we have the set omega, which is the annular domain, which is here. This can be done also in any dimension Rn, and call gamma j the boundary, which is gamma 1 is the small boundary and gamma 0 is the outer boundary. But of course, one can reverse the problem. One can have a Cauchy data given on gamma 1 and solve beginning with gamma 1. The result is exactly the same kind. Okay. So in order to see for what sort of data F0, G0, the Cauchy problem 20 can be solved, we are going to decompose. Okay, first, this is the result. So denote by alpha the ratio R1 over R0, which is a number between 0 and 1. Okay. And for K in Z, denote by F0K the Fourier coefficient of the function F0 on the boundary, and G0K, the same thing for G0. Okay. And then we define the space H of alpha, which depends on this ratio alpha, as being the set of function F0, G0, which are in H1 half times H minus 1 half, such that this quantity is finite. Okay. So the first part is just the norm of F0 in H1 half. The second part is a compatibility condition between F0 and G0, which is of the same type as before. Before, for the rectangle, we ended up with a factor which was like K times sine hyperbolic of KL. Okay. Here we have a coefficient alpha to the power minus 2K. But since alpha is less than 1, this number alpha to minus 2K is a large number as K increases. Okay. So this means that the difference F0K minus this quantity G0K must be quite small if we want to be able to solve the Cauchy problem. Okay. So this is the space H alpha. This is the set of F0, G0 such that this quantity is finite. Then the problem, which is here, 20, the Cauchy problem, has a unique solution if and only if F0, G0 is in H of alpha, and we have these estimates. So the problem becomes well posed for Cauchy data which are in the set in the space H of alpha. Okay. So the idea of the proof is again by using Steklov-Poincare operators in the following way. First, on each boundary, gamma 0 and gamma 1, we define lambda j uj equals to g, excuse me, here is lambda j fj, okay? Lambda j fj with duj over dn, where uj is the solution of this problem, okay? uj is the solution of this problem. So for instance, for j equals to 0, u0 is equal to 0 on gamma 1, and u0 is equal to f0 on the boundary, okay? So in this way, we have two Steklov-Poincare operators which are acting on the space L2 of gamma j. Now, we consider also another Steklov-Poincare operators, which is going to send functions which are defined on gamma 1 into functions which are defined on gamma 0. So lambda 1, 0, so it maps h1 half of gamma 1 into h minus 1 half of gamma 0, is lambda 1, 0 of f1 equals du1 over dn. Okay, so we solve u1 equals to f1 on the small boundary gamma 1, and we compute its normal derivative on the larger boundary. Okay, so we have now three Steklov-Poincare operators which are going to help us to analyze the result. So you see now a solution, a possible solution of this problem can be viewed as something which is harmonic in omega. U is equal to f0 on gamma 0, and u is equal to f1 on gamma 1. Okay, so we have to find what f1 must be. So we can write u as u0 plus u1, where uj satisfies this equation. Okay, now in order to solve the Cauchy problem for u, we need to have g0 equal to du over dn. So g0 is going to be du0 over dn. This quantity was denoted by lambda 0 f0, and du1 over dn, and this quantity was called lambda 1, 0 of f1. You see, this is the equation 24, and this is equation 22. So you see now the solution of 20 exists if and only if we can find a function f1 in h1 half such that lambda 1, 0 of f1 is equal to lambda 0 f0 minus g0. So this means that the compatibility condition on the Cauchy data is that lambda 0 of f0 minus g0 must be in the image of the operator lambda 1, 0. Okay. So in the general case, that is, if we take just a domain which has a boundary with two connected components, the same analysis can be done, and the result is the same. The necessary and sufficient condition in order to solve the Cauchy problem is that lambda 0 f0 minus g0 belongs to the range of lambda 1, 0. Okay. But now what happens in that is that in the case of the annular domain, we can characterize the range of this operator lambda 1, 0 in h minus 1 half in terms of the Fourier series. Okay, and this gives exactly what is stated in this theorem. The range of the operator lambda 1, 0 is precisely the functions such that this quantity is finite. This sum is finite. Okay, so this gives the end of the study for the annular domain. Okay. Now, just for the the few minutes I have, I give the idea of the proof for the Lagrangian control, in which so let me maybe recall what was the Lagrangian control. So the Lagrangian control is that we want to fix a normal derivative on the set gamma such that the normal derivative of the solution of the harmonic function psi is equal to h or approximately equal to h for a given epsilon. Okay. So in order to do that, we are going to define to use two Poincare-Steklov operators, which are the following. First, we denote by omega 1 the set omega minus omega 2. So it is the exterior of omega 2 in the set omega. Okay, so this is the set omega 1. Okay. For a given psi defined on the boundary, on the small boundary, on the red boundary gamma, small gamma, we find a function which is harmonic in omega 1. So psi is not defined in omega 2. Psi is just defined in omega 1. And we assume that its mean value is equal to 0 and the normal derivative on the big boundary is equal to 0. Okay. Once this is done, we define lambda 1 of psi, the restriction, the trace of the function psi on gamma. Okay. So in fact, this is the operator which maps Neumann boundary condition into Dirichlet boundary condition. Okay, so maybe one could call it also Dirichlet to Neumann to Dirichlet instead of Dirichlet to Neumann. Okay, so this is the first Steklov-Poincare operator. The second one is when we solve for a function phi, which is defined on gamma, we solve minus Laplacian of z equal to 0 in this domain omega 2. Okay, so zeta is defined only in omega 2, while the function psi was defined only outside omega 2, and z is equal to phi on gamma. So the second operator is a Dirichlet to Neumann, which is lambda 2 of phi equal to d zeta over dn. Okay. Now, for phi belonging to h1/2 of gamma, we define T12 as being T12 as being the identity plus lambda 1, lambda 2. Okay, so lambda 2 is this operator, and lambda 1 is from the Neumann condition, we end up with the Dirichlet condition. Okay, so first we show that this is a homeomorphism. Okay, this is a lemma which is not. It's not very difficult. This is due to the fact that, in fact, the operators lambda 1 and lambda 2 are positive operators somehow. And we are considering identity plus lambda 1, lambda 2. Okay. And because of this, one can show that the operator T12 is positive. See, identity plus something which is the product of two positive operators. Okay. Well, so once this is done, for the proof of theorem 1, so the theorem 1 says that the image of the operator lambda gamma, which is here, is dense in h minus 1/2. first we assume that we are in a favorable situation. So we want to prove that the range of lambda gamma is dense. Since the range of lambda gamma is the orthogonal of the kernel of its adjoint, we have to show that the kernel of the adjoint is equal to 0. Okay, so this means that lambda star gamma is injective. Okay, since this operator lambda gamma star is an operator which maps h minus 1/2 of the small boundary into h minus 1/2 of the big boundary, not the big, of the control boundary, of the boundary which is here, it is not easy to describe this operator explicitly in terms of solving elliptic problems. Okay, so we assume that we have this situation. Gamma, capital gamma, is the boundary of a small domain, a ball, for instance, and we want to find a Neumann condition on the set gamma such that here we have what we want. Okay, so in order to prove that this is the operator lambda star gamma, which is here, is injective, we solve. We describe first this operator lambda star gamma by decomposition. Okay. First, we show that the operator lambda gamma v applied to phi can be written in this way. Okay. So this is a technical verification. This is not difficult, but this allows us to show that, in fact, the operator v times psi can be written, v applied to psi can be written in this way. So here we have lambda gamma star, for which we want to prove it is injective, and we have this operator identity plus lambda 1 lambda 2, which is a homeomorphism on h1/2 of the small boundary gamma. Okay, so this is an identity. Once we have this identity, we assume that now we have some function phi tilde such that lambda star gamma of phi tilde is equal to 0. Okay, so this means that if this quantity identity plus lambda 1 lambda 2 phi is equal to phi tilde, we have for all v in h minus 1/2 of gamma, v times psi equals to v times this equal to 0, because we are assuming that lambda gamma star phi tilde is equal to 0. Okay, so if this is equal to 0 for all v in h minus 1/2, this implies that psi is equal to 0 on gamma. Okay, and since the function psi is solution of this elliptic problem, from this we deduce that the normal derivative is equal to 0 on the boundary, and since psi and its normal derivative are equal to 0, we deduce that by unique continuation principle that psi is identically equal to 0 in omega 1, where it is defined. So this function psi is equal to 0 here. Now since psi also is equal to 0, because psi is just the normal derivative of psi on the boundary. Okay. So if this is equal to 0, this means that lambda 2 of phi is equal to 0, because we defined psi as being minus lambda 2 phi. So this is the definition of psi. Well, then this means that if we solve minus Laplacian of z equal to 0 in omega 2 and z is equal to phi on gamma, we have lambda 2 of phi d, which is the normal derivative of dz over dn, which is this guy, is equal to 0. Okay. So this means that minus Laplacian zeta is equal to 0 and the normal derivative is 0 on gamma. So this means that zeta must be a constant. Okay. So if zeta is a constant, then phi is a constant on gamma. And since its mean value is equal to 0, then we have phi is equal to 0. And if phi is equal to 0, then the definition of phi implies that phi tilde is equal to 0. Okay. So this means that the kernel of lambda gamma star is reduced to 0. Okay. So finally, for the general case, the generals can be treated by using this figure. In fact, we want to find something on this set gamma. So we extend our domain by adding a part to this set, and we solve first beginning with this set omega, small omega, and then we get the restriction of what we have found for the control on the set gamma. So this is the classical method to find. Okay, so I think I have talked too much, so I can stop here. Okay, so thank you for your attention. Okay, so
thank you very much for your nice talk, Otared, as always. So I don't know if somebody has a comment, a question. Enrique.
Okay, before all, thank you very much for your talk, for your very nice talk. It was very, very clear, so congratulations and thank you. I would like to know something about the limitations of the results. I mean, when you are speaking of the well-posedness of the Cauchy problem, at which level can you extend this result? It has to be always the Laplacian, it has to be always a rectangle or a ball?
No, okay. So depends. Okay, depends what one means by characterization of the set of the Cauchy data. Okay, if one wants a characterization in terms of the Fourier coefficient in some Hilbert basis, this is our method does not allow to treat all kinds of domains. We can treat a rectangle or an annular domain, etc. But if one understands by characterization something of the type, so let me Cauchy problem in a ball. If one wants a characterization in terms of ranges of operators, then this can be done for all domains, in fact. Okay. For all excuse me, not for all domains. For all domains for which the boundary has at least two connected components. Okay. So if you have, for instance, you take a ball and you punch several holes in it. Okay. And you want to solve the Cauchy problem by giving the Cauchy data on one of the boundaries. In this case, one can find a characterization of the Cauchy data in terms of this condition, that lambda 0 f0 minus g0 must belong to the range of a certain Poincare-Steklov operator. Okay, but we cannot give a general result in terms of some Sobolev space or something like that.
Okay. In this direction, and for the Stokes system, is it possible to do more or less the same? Or?
Okay. Okay. The abstract part, yes, but not the quantitative result, which says that you have something like this, something like this condition. Okay. Because for the Stokes problem, you can also have exactly the same analysis of Steklov operators, Steklov Poincare operators, okay, and the same conditions can be done. But for the Stokes operator, I'm not aware of the behavior of the eigenvalues of the Steklov operator. You see here, let me see the eigenvalues. Yes, you see here, for the rectangle or for the annular domain, one can compute explicitly the eigenvalues, okay? And one knows that eigenvalues behave like K, etc. in any domain, in fact, okay? So using this, we can give a quantitative condition. But for the Stokes problem, I don't know if this can be done. Even for a rectangle, for instance, can one compute explicitly the eigenvalues or not? I don't know. In fact, I haven't looked at it. Okay. But apart from this, if instead of the Laplacian you have a self-adjoint operator which is minus divergence of A of x grad of u, okay, the same thing can be done. Because in that case, again, you can associate an appropriate Steklov Poincare operators and Steklov eigenvalues, everything. Okay, this can be done. And in that case, again, for instance, in 2 dimension, one can show that the growth of the eigenvalues is like K, like exactly the same. Of course, the eigenvalues are not known, but one can give the rate of growth of the eigenvalues.
Okay, and finally, a third question. Regarding the Lagrangian control, you can get the approximate controllability result. Can you complete this with some kind of exact finite dimensional controllability? Can you have the same time approximate controllability and exact controllability in a finite dimensional space, for example? We cannot hear.
You cannot hear? Oh.
Now, yes. Now, yes.
Now, yes.
Now, okay, it was because my I don't know how to call it, free, but I don't know. They are discharged. They don't have batteries enough. Okay. So you see, we what we prove. Oh no, it's not here. Excuse me. It's here. You see, we prove that if you solve this problem, Laplacian psi equals to 0 in omega, d psi over dn equals to v on gamma, and the psi over dn equals to 0 on the omega minus gamma, then the operator lambda gamma, which is defined here, okay, it has an image which is dense, okay? And this is done by proving that the adjoint of lambda gamma is injective, okay? So it's an abstract result. We cannot estimate how well we can approximate a certain V, okay?
No, but yes, I know, but I mean, if you fix a finite dimensional subspace
yes,
of h minus 1/2, can you have at the same time that the range
okay.
contains?
Yes, I see.
Space.
I see. I don't know. But this is a good question.
With,
Yes.
with the compactness argument or something.
Yes,
like
yes, I understand. Yes, yes. I don't know. I don't know, but this is a good question. Yes, yes. So you imagine that you take some finite dimensional space, say capital X dimension M, and you want to find another space in the for the V such that oh yes, this is no, I don't know. I don't know, but this is a good question. Yeah.
Okay, thank you very much.
Okay.
So Laurent Bourgeois.
Is there still time for a question and a comment?
Yes.
Okay.
For me, there's no problem.
Okay, thank you. Yes, it was a very nice talk. I have a question about the annular case.
Yes.
I'm not sure I have well understood. It seems to me that in your example, the support of the Cauchy data is gamma 0, which means the outer circle. Right?
Exactly. Yes.
But can you do the same analysis if gamma 1 is the support of the Cauchy data?
Yes, yes, yes.
Is this exactly the same?
Yes, and you find exactly the same type of conditions. Okay.
Okay.
Yes.
So it seems to me that your compatibility condition is very interesting because it was for me an open problem to quantify how the instability of the Cauchy problem depend on the size of the support of the data. I mean here gamma 0. And what I find very interesting in your compatibility condition is that alpha in fact reflects this size because it's the ratio.
Exactly. But it's in fact it's yes, you're right. In fact, what is important is not really the size of gamma 1 or gamma 0, is the ratio between the two. It's the aspect ratio of the annular domain which is important.
And it seems to me that it is the first time that we emphasize we quantify in fact the impact of this ratio on the instability of the Cauchy problem, and it would be very interesting to generalize this kind of compatibility condition to more general.
You see, for the rectangle, it's also the same. You see, for the rectangle, the condition is. Where is it? Again here. The rectangle, in fact, it doesn't matter how the size of the base of the rectangle. What is important is that the height of the rectangle. You see here, you have exponential of KL. Okay? So it's the same thing.
The same, yes.
This means that when you begin to solve something, the farther you go from the boundary, the more you have to pay. The cost, the higher is the cost. Okay, and the cost is something of exponential of KL. Okay.
Yes, it's of exponential type because it's
yes, exactly.
Cauchy problem is a exponentially ill-posed problem.
Exactly.
Another interesting question would be to analyze the type of noise on the Cauchy data that would preserve the compatibility condition.
Oh, yes. For instance, for the ball, you see.
Which kind of noise will perturb F0, F, and G, so that the compatibility condition is still satisfied?
Okay. You see, if the noise attains only F0, then everything is destroyed. Somehow you have to make the noise on both F0 and G0, on both, okay? Maybe one can have, I don't know whether, how is it possible to write it? Okay, I don't know.
Okay, but thank you very much. This was very
okay. Yes, but this is a nice question. Yeah, yeah, this is a nice question. You're right. Okay, thank you for your attention.
Well, I think we are out of time. So thank you very much, Otared, for your nice talk.
Thank you for the invitation and your kind attention.
Thank you. And see you
so a little bit later, I'm going to fix the small mistakes I noticed, and then I give you the PDF of the file.
Yes, please. Thank you very much.